We're looking at a problem last time that I believe was tangent of theta plus pi. You by chance have that one? I figured out what I was doing wrong.
Yes, it's right here in front of me.
And that's supposed to equal what?
Tangent, it was tangent theta plus pi over 4.
There's another problem. Okay.
And then cosine theta plus sine theta over cosine theta minus sine theta.
All right. Let's start with this. First of all, let's start with the identity. We know we're looking at a sum and difference thing. What's that equal to? And this is where I made a mistake.
Isn't it tangent A, tangent B?
It's tangent A plus or minus tangent B, all divided by 1 minus or plus tangent A times tangent B. Now, you understand what I mean when I say plus minus or minus plus?
Yes.
It means basically that I can erase that minus sign, I can erase that minus sign, and I can erase that plus sign. So, in this case, what does that translate to? In other words, I want to take this, and using that identity, what does it become?
It becomes tangent theta plus tangent pi over 4.
Which is 1.
And then 1 minus tangent theta 1.
Yeah. So that is really the first step. Okay. So let's erase what we have and replace it with this thing on the bottom right. So I want to do tangent theta plus 1, all divided by 1 minus tan of theta. And the way we did it yesterday is really the correct way to do it, which is to convert everything to sines and cosines.
Right.
Okay? Even though the more complicated, well, actually they're both the same complicated. They both have two terms in the denominator and 2 terms in the numerator. So you could actually make an argument that the left side is as complicated as the right side. Okay?
Right.
So turn everything into sines and cosines. That's the first tangent theta. Now, add those two together, what do you get?
You get a. I have.
How do you add 2 fractions?
Oh, you have to convert it to a fraction. So,
Okay, so what's 1 become?
Doesn't 1 become 1 over 1?
Becomes cosine over cosine. In other words, in order to add these 2 fractions, I need a least common denominator. And it's going to be cosine. So the numerator becomes sine of theta plus cosine theta all over cosine theta. So that's the numerator. Do the same thing with the denominator. What do you get?
Sine over cosine minus, or sine minus cosine all over cosine.
Well, this is going to be cosine over cosine. So the bottom becomes cosine minus sine all over cosine.
Okay.
Okay. Flip and multiply. Gets rid of that, and you're left with that, which is that.
Oh, cool.
And that's all you have to do is turn the left into the right. And that usually always works as a last resort, converting everything to sines and cosines. It's not always the best way to verify these things. Some of them, there are other tricks. Some of the more difficult ones, you have to, one that's particularly common is what to do when you get stuff like this. Or this. Or this. Or this. Trig doesn't have any identities that are equal to these.
Mm-hmm.
So when you run across one of these, you want to multiply by its conjugate. That's one of the secret, not secret, but one of the techniques that's most valuable in verifying trig identities is when you run across one of these four things, know that you're going to have to multiply by its conjugate. And the reason is that when you multiply by its conjugate, you end up with 1 minus cosine squared, which is sine squared. So you can take these two terms and turn them into 1. So that's the thing to look for. You have some other trig verifying problems?
Yeah, I do.
Let's tackle them. These can be tough, they can be medium, they can be easy. That last one was actually pretty easy. Where I screwed up yesterday was not remembering the identity for tangent of a plus or minus b.
Let's see. We can do. All right, let's do sine theta minus cosine theta over sine theta plus cosine theta minus sine theta all over cosine theta equals 2 minus secant theta cosecant theta.
Like that?
Yeah.
Okay. We can certainly turn the right side into sines and cosines, right? Because secant theta is just the reciprocal of cosine, and cosecant theta is the reciprocal of sine. So we could do it that way, but let's start off by adding those two together. Again, you're adding fractions. So what is the common denominator going to be?
It's going to be cosine sine.
Yeah. Okay, let's do it that way. So sine theta, cosine theta. What goes in the top left?
The top left.
The easiest way to really do these is I'm going to show you how. In other words, don't distribute. Leave it like that.
Okay.
The reason is that it's really easy to tell that that's the same fraction, right? The cosine thetas cancel, and I'm left with sine minus cosine over sine.
Yeah.
So I don't distribute this top. Okay, tell me what the right side is equal to. It's going to have the same common denominator.
And then it's going to be cosine theta, sine theta, in parentheses, and then sine theta on the outside.
Yeah. Okay, now let's distribute. So the top becomes sine theta minus, sine theta cosine theta minus cosine squared of theta plus sine theta cosine theta minus sine squared of theta all over sine theta cosine theta. Okay? Now I'm going to make some room. Keep writing. I'm going to change the color so we'll know we're not starting at the top. So what do we have down here? We have 2 sine theta cosine theta, right? There's one, and we're adding another one. And then we have minus. Notice that this becomes cosine theta plus sine squared theta. I've got
so it's
this
one,
and I've got this one. But if I put them together like this and put the negative sign out front, that's the same. In other words, is all I've done is gathered like terms, right? Okay. All over sine theta cosine theta. With me?
Yeah.
And this has got to equal that thing over there on the right. Well, it will. One thing about verifying trig identities is they don't ever give you ones that aren't trig identities. They only give you ones that are. So you never have to worry that it doesn't match. You just have to figure out how to get it into that form. What's cosine squared plus sine squared equal to?
1.
So now I have 2 sine theta cosine theta minus 1 all over sine theta cosine theta. Let's split this into 2 fractions. The 2 fractions being, that's one of them. That's the other one.
Yeah.
Okay. When I put the first fraction, I get 2 sine theta cosine theta over sine theta cosine theta. That's just the number 2.
Yep.
When I split the other one, I get 1 over secant theta, sine theta cosine theta. You with me?
Yeah.
This turns into that because the reciprocal of sine is cosecant and the reciprocal of cosine is secant. So this whole thing becomes 2 minus secant theta cosecant theta. Bingo.
These are actually much easier than I thought.
What it really is just algebra. As long as you know your identities. If you know your trig identities, the rest of it is just algebra. So you've got to be good with adding fractions, subtracting fractions, finding least common denominator, things like that. What else you got?
let's see. Let's do 3 cosine theta minus 4 sine theta squared.
Squared like that?
Sorry, the whole equation.
Ah.
So parentheses squared. Yeah, sorry.
Okay.
And then plus parentheses 4 cosine theta plus 3 sine theta squared.
Like that?
Mm-hmm. Equals 25.
Well, good. I didn't have any more room to write, so I'm glad it's just a simple one. Okay, what are we going to do here? What's the only thing you can do? When you don't know what to do the only thing you can do.
Distribute the exponent.
Square both terms.
Yeah.
That's the only thing we can do. I can't do anything else, but I can square this. So when I square the first term, what do I get?
You get 6 cosine theta plus, or sorry, 9 cosine theta plus 16 sine theta.
Actually, you get 9 cosine squared theta.
Squared theta, yes.
Minus 2 of this times that, which is 24 cosine theta sine theta, plus 16 sine squared theta. In other words, all of that comes from that right there. You with me?
Mm-hmm.
Now I'm going to square the next one. What do I get?
You get 16 cosine squared theta. Then, isn't it, what am I trying to say here? 18 sine.
Here's the thing to remember. A plus b squared is always a squared plus 2ab plus b squared. Okay? So what's 2ab?
Oh, 2ab's, it's, so 24.
Uh-huh.
Yeah.
24 sine theta cosine theta. What's the last term?
B squared, 9, yeah, 9 sine squared theta.
Okay. Now, remove the parentheses, that goes away, right?
Right.
And you end up with 25 cosine squared theta plus 25 sine squared theta. Now what can you do?
You can,
Factor.
yeah, factor, so it's 25. I see where, yeah.
And that's the number 1, so you get 25 equals 25. And there really is not any easier way to do that problem. You got to do every step we did.
Yeah, it's a gross one.
Some of these trig identities, there are easy ways to prove them and there are difficult ways. And you can't always know when you start it out which is the easy way and which is the difficult way. So you kind of try to start it out at the easy way, but it's easy to go off on a wrong path in trying to solve these. And if you happen to go off on the wrong path, you get lost in the trees and you can spend 20 minutes trying to solve it and you're not getting anywhere.
Yeah.
You end up having to go back and start the whole thing from the beginning using a different path. Like I said, the one thing they tell you is that if all else fails, convert everything to sines and cosines and go from there.
Alrighty.
What else you got?
Let's do these since I don't really actually understand these. So it says here we have to like figure out what the right side of the identity should be.
Okay. Give me the left side.
The left side is parentheses secant x plus tangent x. Timed or multiplied with parentheses secant x minus tangent x.
Divided by, did you say?
Multiplied, sorry. It's just another parenthesis set, yeah. Secant x minus tangent x.
Okay.
All over secant x.
All right. Good one, because we're not going to solve this by converting it to sines and cosines. We could, but there happens to be an easier way. And that is, if you multiply the two numerators together, what do you get? Notice you're looking at the difference of squares, right?
Right.
So what does that become? That becomes secant squared x minus tangent squared x. That's the numerator.
Mm-hmm.
Now, the other identity that you really need to remember is tangent squared of x plus 1 equals secant squared of x. So what does secant squared of x minus tangent squared of x equal?
1.
So the right side now becomes this. And there's another convention where you don't leave a trig function in the denominator if you can put it in the numerator. So what does that become? Yeah, cosine of x.
Cosine of x.
So that's the right side. And
so
I did not convert these things to sines and cosines. I used that second Pythagorean identity, which is what you generally want to use when you're looking at secants and tangents, is you want to be able to use that identity. Tangent squared plus 1 equals secant squared.
Right.
Especially when you see that. Because you know, when you multiply that times that, I'm going to get this, and that's an identity. That's equal to 1. All right, what else you got?
We'll do some more of those. Secant squared x cosecant x. All over secant squared x plus cosecant squared x.
And again, they don't give you the right side?
Yeah.
Okay. Well, let's see. There's no identity between secant squared and cosecant squared, so I'm not going to use that. But since I can't see a different way to do it, I'm going to convert everything to sines and cosines and do the algebra.
Okay.
Okay. So secant squared is 1 over cosine squared. Cosecant is 1 over sine. So that's my numerator. My denominator is 1 over cosine squared x plus 1 over sine squared x. So now I've turned everything into sines and cosines, and now it's just algebra. What's the top? In other words, what does that become? You didn't leave off anything, did you? All 4 of these are not supposed to be squared, correct? The numerator is secant squared times just cosecant?
Yeah.
There's no square on the cosecant?
No.
Okay. So, what's the new numerator?
The new
numerator.
The common denominator is cosecant squared x sine x.
No. If I'm solving that, oh, excuse me. We're multiplying. Thought we were adding for a moment.
No worries.
Okay. And then the bottom. What's the denominator of the bottom?
The bottom is cosecant squared x plus sine squared x.
Yeah, you said cosecant. I think you meant
cosine.
Cosine. Yeah. And they're going to be multiplied. Because when you find a common denominator, you multiply them. That's how you find the common denominator. Now, what goes in the numerator of the denominator?
The numerator is sine squared x plus cosine squared x. That's what I got.
Notice that you always end up getting something that turns into 1. Okay? That's 1.
Mm-hmm.
Now, flip and multiply. What do you have?
So you flip and multiply, then you have cosines. Oh, you just have 1.
That's what you have right there.
Oh, yeah, I forgot we don't have an exponent on the
Flip and multiply, the cosines cancel. You get sine squared over sine. That's equal to sine. Well, when they don't give you the right side, it usually comes out to be a single trig function.
Yeah.
Just like these last 2 have. Okay, what else you got? Do you have any that you're looking at something like this? Or sine x, anything like that? Because these require a little special trick that you kind of have to know about.
I have one that's 1 minus cosine squared.
Well, that's easy because that's just sine squared. You don't have to use that trick for that.
Oh, here. So 1 minus cosine theta.
Go ahead.
All over sine theta equals cosecant theta minus cotangent theta.
Like that?
Yes, sir.
Okay. Here's where I'm going to do that trick. And that trick is, you wouldn't think of this if somebody didn't point it out to you. In other words, I'm not allowed to use algebra to solve these. I can't multiply both sides of this equation by sine x. It's one of the things they don't let you do when you're verifying trig functions. However, what they do let you do is multiply by the conjugate, which is this. In other words, all I'm doing is multiplying the left side by the number 1. Right?
Mm-hmm.
What that gives me in the top is 1 minus cosine squared of x. And that's beautiful because that converts to a single term, sine squared of x. What it gives me in the bottom is this. Don't worry about this yet. Don't distribute it for sure. But you can see how the left side became this?
Yes.
What's the top turn into?
It turns into sine squared.
And now I can take that sine squared and cancel out that sine and that square. So what I end up with is sine of x all divided by 1 plus cosine of x. Now, notice what the right side is. It's 1 over sine x minus cosine over sine.
So 1 plus.
Which is 1 minus cosine all over sine. Now, that might not look like an identity, but trust me, it is. We still have some work to do to get it into it, but it is. That's a common one that most people are puzzled as to why that's an identity, because it looks different. All right. I'm not sure I've done this the most efficient way, but I can certainly prove this bottom right identity. And I'm going to do it. Notice that if I could manipulate it algebraically, I got cross multiply it, you got sine squared of x equals 1 minus cosine squared of x, right?
Mm-hmm.
Well, that's an identity. 1 minus cosine squared of x is equal to sine squared of x. So we know it's true, but we can't use that. You can't get away with doing that in trig class. They won't let you do that. So what I have to do is the same thing I did already. Multiply the left side by what?
By 1 minus cosine.
Over 1 minus cosine. In other words, I can only multiply it by the number 1. So I got to have the conjugate in the top and the bottom. And now this gives me 1 minus cosine x in the top times sine x. And in the bottom is going to give me 1 minus cosine squared x, which is sine squared x. Now I can cancel that with that, and that's what I have over here. 1 minus cosine all over sine.
So
now, in case you're worried about the fact that I worked on both sides of the equation, I didn't particularly have to. In other words, I could have taken this answer I got, I could have worked strictly on the left side and gradually turned it into cosecant of theta minus cotangent of theta. It's just that by messing with the right side, I can see better how to do it. And there really aren't any rules against messing with the right side. You can do that. You just can't use algebra on cross multiplying or doing stuff like that, or dividing both sides by cosine x or anything like that. You can't use that technique. But this technique right here is a very common technique. You're going to want to use that a lot, where you multiply by the conjugate, because that turns this into something that is far more workable. It turns it into 1 minus cosine squared, which turns into sine squared. So I've taken these two terms and turned it into one term. merely by multiplying by the conjugate on top and bottom. So remember that trick. That's one of the primary tricks that you're going to use on some of these. And that's not turning everything into sines and cosines. In other words, that's kind of a different method. Another one.
A completely different method, yeah.
Well, yeah, in a way. In other words, you got a lot of choices on these things. One way is to turn everything into sines and cosines, but if you've got stuff like tangents and secants, it's really going to be a big pain to turn them all into sines and cosines. Then your algebra really is going to be tough. Whereas it's easier to use that tangent Pythagorean identity. So when you see tangents and secants together, think that tangent squared plus 1 equals secant squared. That's the identity. It's just like when you see sines and cosines, the identity you're thinking of is sine squared plus cosine squared equals 1. So you're always using those identities to help you with these. Got another one? We got
yeah.
about 10 minutes. We got time for one more.
Let's see. Let's do cosine x over 1 minus sine x plus 1 minus sine x over cosine x equals 2 secant x.
Okay. Now, rather than doing what I suggested you do every time you run into a 1 minus sine or 1 minus cosine, let's just add these two fractions together.
Okay.
What's my common denominator?
1 minus sine parentheses cosine x.
Goes in the top left.
Cosine squared x, and then
the only thing I'm concerned with is that is the same as that. And I can see that it is. Okay. So what goes in the top right?
Let's see. It's 1 minus sine squared.
Well, it's 1 minus sine x, all of it squared, which is not quite the same thing. Yeah, that's a little different. Yeah, times that, right? In other words, this fraction right here is equal to that fraction. I believe, right?
Yes, sir.
Okay. So now we have to carry out this squaring.
So it would be 1 minus or plus actually. Minus.
No, you were right. It's minus.
I was right. It's minus.
Uh-huh.
So 1 minus sine x, just sine x, isn't it?
2 sine x.
Or 2 sine x.
Plus
sine x.
Sine squared x.
Sine squared x, okay.
In other words, you're expanding 1 minus sine x. Okay. I'm not going to mention the denominator yet. Let's simplify the numerator. I see a cosine squared x and I see a sine squared x.
That's 1.
Okay, and there's already a 1 there. So I got 2 minus 2 sine x. all over
sine x cosine.
secant x is 1 over cosine.
Oh, so the sine cancels out, and the two.
Actually, it
two,
doesn't yet. Factor out a 2 from the top. There you go. I think that's what you were probably trying to say, right?
Yeah.
In other words, it's going to equal 2 times 1 minus sine x, that's the numerator, all over 1 minus sine x times cosine x. And now I can cancel that with that. That's why you normally don't distribute when you see something multiplied together.
Mm-hmm.
In other words, had I distributed the denominator, I would have just made it harder to see. Well, now I got 2 over cosine x, which is 2 secant x. You see what I'm saying? In other words, had I multiplied the cosine x times the 1 minus sine x, then I would have had to factor it in order to be able to cancel out with that. So don't multiply them together unless you're out of other things to do. Leave them factored, because almost always one of them will cancel out with something you find in the numerator, just like what happened in this case. But it wasn't easy. I had to factor out a 2 from that, and I had to notice that.
Yeah.
And that I was going to be left with 1 minus sine x, which is perfect because I got a 1 minus sine x in the denominator also. So generally, the solution to all of these problems is just do the algebra.
Yeah, just factor.
It's not easy algebra. It's fairly tough algebra, but that's what you have to do. Want to try one more?
Yeah.
These actually get kind of fun once you get used to doing them.
Yeah, I just
like
need
a
to practice them.
Once you can solve it, they're fun to solve. They drive most people crazy, but once you, and there really is only one purpose of these, Nico. There are not real life problems where you have to verify the left side is equal to the right side. There are no real life problems for that.
I figured.
They came up with this exercise to teach you your trig identities. That's the only purpose of these.
Well, now that you say it like that, it kind of clicks in my head a little bit.
It accomplishes that. You do about 10 of these things, and by the time you're done with them, you know all your trig identities beautifully. It does exactly what they're trying to do. You can't work through these verifying trig identities without knowing your trig identities. And as you use them, you memorize them. And really, they're only talking about the 11 main identities. You got 6 reciprocal identities, you got 3 Pythagorean identities, and you got 2 quotient identities. In other words, tangents equal to sine over cosine, and cotangents equal to cosine over sine. Those 11 identities are the only ones you need to solve these problems. Those 11. Well, that's not quite true. The very first one you gave me required sum and difference formula for tangent.
Right.
But once you use that, then verifying is primarily those 11 identities. What's that another? Let's do one more real quick.
One more. So we got tangent x plus tangent y all over 1 minus tangent x multiplied tangent y.
Okay, tangent x plus tangent y all over what?
1 minus tangent x multiplied by tangent y.
Like this?
No, it doesn't have the parentheses. Sorry.
Aha.
I should have just said tangent x.
Actually, I was just going to tell you, I bet there's no parentheses. Why is that? Why are there no parentheses there?
Is it because you can't multiply tangents?
No? What does this look like?
Oh, the same.
That's the sum and difference formula, only it's the right side. So what's that equal to?
Equal to, oh, yeah. Tangent plus x.
No, just x plus y. In other words, if you started with that, you would use this using the sum and difference formula. So what they've given you is the identity, only you need to be able to go both ways on these things. In other words, if I told you, what is this? Cosine x cosine y plus sine x sine y, what's that equal to?
Isn't that cosine x plus y?
Minus y.
Or minus y.
Remember, on the cosine one, it's opposite. On the sine one, it's the same. And incidentally, one way to memorize this tangent identity that I got wrong yesterday is remember that tangent is sine over cosine, right?
Right.
Well, sine, the sine is the same in that identity. And it's sine over cosine, and in cosine, it's the opposite. So you can always remember your tangent identity that way. Know that you need a plus in the top and a minus in the bottom. And one way to remember that is it's kind of like sine over cosine. And sine, you have the same sign in the top, and in cosine, you have the opposite sign, whenever you're doing these sum and difference things. So this is the answer right there. Okay?
Yeah.
Nico, you good to go for tonight?
I am.
Okay, let me give you just a little bit more information. You ask how you can schedule an appointment?
I actually figured it out.
Okay, make sure you use this website. And the only reason I say that is because this website is much easier to use than my other one. The other one is Algebra to Calculus Tutor.
Okay.
This one, they both use the same scheduling program, but this one makes it easier to pay, makes it easier to schedule. Everything about it is easier. And if you go onto that website, look up scheduling an appointment, it'll show you my complete availability and let you pick a time and date.
Awesome.
And you don't have to worry about necessarily paying for it when you schedule a session. I'll go ahead and just invoice your mom or your dad.
Okay.
But that's how you do it.
Awesome.
So,
thank you, David.
You're welcome. Thank you, Nico. I'll talk to you next time.
Sounds good.
Bye-bye.
Bye.
Come on, man.